So iron and a lot of the isotopes we see around us every day are fairly stable. They tend to not decay, they'll just sit there and their nucleus is not changing with time. Other isotopes are less stable. They'll undergo what's called spontaneous decay. So for example, uranium-238, which is a uranium nucleus with 92 protons and 238 nucleons, tends to decay into thorium-234 by releasing radiation. So in a little while we'll be discussing how half-lives relate to how stable a nucleus is. But first of all, let's consider 3 common ways for a nucleus to decay. Nuclei can decay by releasing alpha, beta, or gamma radiation. Now, whenever a nucleus decays, it still obeys the important rules of physics. So in particular, it obeys conservation laws. So there is conservation of mass/energy, that is, it obeys E equals mc squared. If it loses some mass, then it is releasing a certain amount of energy. Linear momentum is conserved. Angular momentum, which is related to the momentum of going around in circles or rotating, is conserved. Electric charge is conserved, so we're not creating or destroying positive or negative charges. And the other thing that is conserved in nuclear reactions is the number of nucleons. So the total number of neutrons plus protons remains constant. So let's start by considering alpha radiation. In alpha decay, a helium nucleus, which is a 4,2He, is released. So one example of this is the decay of uranium-238. So we can write this decay as U-238-92 decays into thorium-234-90Th plus that alpha particle, which is the helium nucleus, 4,2He. So in alpha decay, we always get this helium nucleus released. And so we can write an equation to describe alpha radiation in general, or alpha decays in general. These are known as transmutations because we start with some parent nucleus and it forms some daughter nucleus plus an alpha particle. And so we can write that the parent nucleus with atomic number Z and mass number A gets converted into a daughter nucleus with atomic number Z minus 2 and mass number A minus 4 plus the 4,2 helium nucleus. So you can see here that the number of nucleons is conserved across this reaction. On the left-hand side, we have the number of nucleons is equal to A. On the right-hand side, we've got A minus 4 plus the 4, which are in the helium nucleus, so A. So number of nucleons is conserved. Now let's have a look at the mass energy conservation to work out how much energy is released in the decay of uranium-238 to thorium-234. So the problem is an atomic mass unit U is 1.6605 times 10 to the minus 27 kilograms. The mass of 238 uranium is 238.0508 atomic mass units. The mass of 234 thorium is 234.0436 atomic mass units, and the mass of helium-4 is 4.0026 atomic mass units. Calculate the energy released when uranium-238 undergoes alpha decay to become thorium-234. So the first thing we need to do is write down the equations for what's going on. So we've got 238 uranium. Now because it's uranium, it has an atomic number of 92 and it's decaying into 234 thorium. Thorium has an atomic number of 90 plus the helium. Now what we're going to need to do is work out the mass of the left-hand side and the mass of the right-hand side, and the difference is going to be the mass defect, and that mass defect is converted into energy. So the change in the mass, well, we know it's going to be a mass loss, so we'll write it as the initial mass minus the final mass, and that'll just get rid of that negative sign for us so that we'll end up with a positive answer. So we've got the mass of the uranium-238, so that's 238.0508 minus the mass on this side, which is the 234.0436, plus the 4.0026, and everything here has atomic mass units. So this is equal to 0.0046 atomic mass units. And so now to calculate the energy, we can use E equals mc squared. So this is equal to 0.0046. And now let's get the mass now into kilograms. So we can times this by 1.6605 times 10 to the minus 27 kilograms. And then times c squared, so 3.00 times 10 to the 8 all squared. And this gives us 6.87 times 10 to the minus 13 joules. Now, as we said before, electron volts are a more useful unit. So the energy in electron volts we divide by 1.602 times 10 to the minus 19. And that gives us 4.29 times 10 to the 6 electron volts, which is equal to 4.29 mega electron volts. And so that's the amount of energy that is released.